Morning, everyone. I'm Manoj Panicker. I work for Cavium, where we've tried a new way to offload OVS using our LiquidIO smart NIC adapters. And I'm going to talk a little bit about that today. So let's start with the existing model using the software open vSwitch models that exist today, where you run the open vSwitch on the x86 server. You can do that either using the classic kernel mode open vSwitch, or you have the OVS plus DPDK acceleration available today. Both ultimately is trying to get packets into the VM, and then you do some useful work, and it's got good traction in the community. But there are some limitations with this model, and the main thing is that you're consuming x86 server CPU cycles in trying to move packets from the network into the VMs, right? And that's a big cost. What that does is it prevents CPUs being available to run VMs so that the workloads can be efficiently handled. And also the fact that as your pipe grows bigger, the network connectivity grows bigger from 10 gig to 25 to 50, you're going to end up using more host CPU cores just trying to move the packets to the VMs, right? And customers want to find a solution to these problems, right? And not only do they want to solve these problems, folks who have worked with Cavium also have interest in certain additional features that they're looking at, right? And one of them is with the ability to manage the vSwitch without having to run it on the host, right? So that there's remotely managed, and one of the main drivers for this is that the host may not be in the control of the customer, right? They may be having their tenants manage software on that. They also are looking at doing upgrades without touching the host, right? Obviously, one of the use cases being that it could be in the tenant's hand, but so they cannot manage upgrades. Both those things have been one of the driving factors for Cavium's customers, right? To look at LiquidIO. So obviously, you want to offload to take care of the performance gains, to gain more CPUs from the x86 server. And the prevalent model today is to try to use the VF representers, TC flower-based offload, and try to get the packets switched directly from the NIC adapter directly into the VMs, right? And you do PCI pass-through and get the packets directly to the VM. You save host CPU cycles and try to do that. But in that case, the switch is still in the host, right? You still have the control plane running on the host. You're managing the devices, the connectivity using the host-based vSwitch. The alternative to that is that you do a full offload, right? Not only do you allow the data plane to fully exist within the adapter, but you also get the control plane to exist on the adapter. And in that case, you still leverage PCI pass-through to get the packets into the VM. But now you can manage it remotely. You don't have to go to the host OS to do that. And that's the LiquidIO model that I'm going to present shortly. So what it does effectively is what's going to be shown in this animation here. We have typically in the x86 servers, you'll have the OVS data path, the vSwitch D, the DB server. They all exist on the x86, a mix of kernel versus user space. But the aim of LiquidIO is to move not only the data path and vSwitch D, and I'll talk a little bit about the accelerator part, but you're going to move the DB server and the vSwitch D to exist on the adapter itself. So now you're basically freeing up VMs, freeing up CPUs to allow more VMs to be scheduled on the x86 server. And this is basically the block diagram for LiquidIO's model, right? How we achieve this. So the reason we're able to do that is because we've developed the smart NIC adapter based on Oction's MIPS processors. Cavium has been at the forefront of developing multi-core MIPS processors for the longest time. We use it in a lot of customers use it for their networking equipment. What we have done is taken those processors and built a network adapter out of it, and then we developed the OVS offload application using that. What we have done is it's a multi-core processor, so we have created two sets, one that runs the data plane, and the other runs the control plane. And the control plane is running a version of Linux, right? And that allows us to use the Open vSwitch control plane as is, right? And it supports OVS 2.6 today. What that does is it allows the vSwitch and the DB server to run locally within LiquidIO. It leverages the control, the kernel module, with a DPF net filter, but then accelerates the data path, right? So the traffic to the VMs go through the block that's seen on the left-hand side of this diagram here. That's the accelerated data path. That's implemented using bare metal, Cavium's bare metal application. But we allow communication between the control plane running on the right side of this block diagram here, and there's an implementation of a intercore messaging that allows these blocks to talk to each other, and that's where while we are compliant with the OVS, the open source OVS, we allow an offload to take place between the control and the data plane, and have packets moved through the data plane. We making copies, and I'll talk a little bit about in the next slides. So some more information about how this happens. Like I said, it uses our multi-core processor. What that allows is there are some abilities in the hardware itself to do packet parsing, scheduling of the packets onto one or more cores. It also allows us to implement that messaging layer using the hardware capabilities that is available in the Octeon MIPS cores. At the end of it, you're not consuming any CPU cycles for running OVS or moving packets to the VMs. Now you are able to now do it entirely within the adapter. It does not require any VF representers to exist in the host. All you need is you have to use the LiquidIO VF drivers. Obviously, we are attaching the VFs directly into the VM, and that requires a VF driver in the VM. We can support connection tracking, NAT. There's also ability that we can leverage from the hardware to perform IPsec processing, and I'll talk to you about that as well in a little bit. This is just an animation to show you what happens and how does the intercore communication get leveraged to move the packet as it arrives from the network and how it gets to the VM. So once a packet comes in, it's going to come to the data plane, and obviously it's going to do a lookup in the copy that is in the data plane. When the first packet arrives, obviously it's going to miss. So then we're going to use the messaging layer to send it and have it inspected by vSwitch. It does what it does with looking up in the DB server, or if you wants to talk to an OpenFlow controller, it could do that. Basically, at the end of it, you're going to find that you can add a flow that comes into the kernel. This is all classic Open vSwitch behavior. This is not modified in any way. But once the update happens, then you allow a copy of that flow table to be transferred to the data plane. And now the data plane has a version of the flow table and can switch packets directly. So at this point, any packets that come can now be switched directly into the VM, right? And there are no more traversals to the control plane in this case. That's a typical model. Let's go to the next slide. So we also leverage the same behavior for implementing contract support with our OVS offload. And the path remains similar. It's going to get a packet. It's going to have a mess. It's going to go to the control plane. What changes is that now you're going to force that packet to be inspected by the connection tracking module as well, and make a decision on whether that packet needs to be sent forward or not. So the typical connection tracking rules would say that if a packet's in established state, then you allow those packets to go. So all the decision making still continues to use the kernel's contract module. That stays unmodified. But once that happens, we also make a copy of the connection tracking table now, so that we are able to realize if these flows, if these connections rather are allowed to go to a particular VM or not, and that decision can be made entirely in the data plane itself, right? So that's basic OVS capabilities that LiquidIO provides, but our customers end up using not just trying to offload OVS, there's a definite benefit in trying to do the switching entirely in the adapter and getting the packets directly to the VM for performance benefits. But like I alluded before, there are other gains that can be realized with this architecture. One of the model is what we call a secure access model, where we don't allow the host to intervene with the adapter in any way, right? We seal out the host operating system, so there's no application that can interact directly with the adapter. And we have the ability to have the firmware being managed by a remote agent. This obviously customizes the firmware to allow the customers' control applications to run on the firmware as well, and then they manage the OVS updates that way. There are other use cases where, in addition to the tunneling protocols that we are all familiar with, the customers choose to do things differently, right? And they want to implement their own tunneling protocols. And that is possible by modifying the data plane in that case. Obviously, again, customized firmware. But it allows them to leverage the benefits of running OVS or compatible OVS, but then have their own secret sauce being added on the network tunnels. And we also can do IPsec. The hardware supports crypto acceleration. So we have the ability to basically perform encryption of the packets as they arrive from a VM. We can offload the assays into the adapter and perform encryption operation or decrypt operation for particular flows as they come from the VM. So the PCI traffic is clear text. It comes into the adapter, gets encapsulated, and then the OVS processing takes over, and you can choose to send it with an additional VXLAN tunnel, for example, and then send it out to the wire. So you would send packets in a VXLAN tunnel, but the contents are encrypted in that case. And there are others who have taken the model that we have implemented with LiquidIO with OVS offload, but then they have gone ahead and implemented their own vSwitch. I mean, there are multiple models that exist of their own customers doing their own vSwitch on an x86, and they like this model where it's already available, the skeleton's available, and then they take that and then build their own porting of their vSwitch that they can run on the adapter. So these are some of the customer use cases. Coming back to the OVS offload that we do itself, some performance numbers that I wanted to share with you guys. We tried this with the latest version of the OVS release that we have on a CentOS 7.3 host, and we compared it with an Intel. So you can see that there's definite gains with LiquidIO, that's in blue. And again, CPU utilization, again in blue on the right side. For lower CPU utilization, you get a higher TCP throughput. This is done with the 2 VMs, and we have taken 2 virtual functions and tried to push packets using netperf, right? So that's one of the data points that I wanted to share. The other was using UDP, trying to get to the full throughput, 20 gigabits. So there's a typo on this. On the left side, it says Gbps. That was pointed out to me, so it's definitely gigabits per second. But as you can see that Intel has an edge at the small packets. It can ramp up quickly when you're in bridge mode. Basically, you're not doing any VXLAN tunnels. But LiquidIO can perform better when VXLAN tunnels are in effect. It can do the entire tunnel termination in the adapter itself, and it can push the packets to the VM, right? And this is basically running DPDK test PMD on the VM, a single VM in this case, and trying to see how many packets it can receive at that point. We have the same setup than we running with the Intel X710 in this case, but then running OVS DPDK in the host to move the packets to the VM. So we are also able to integrate the OVS offload solution with OpenStack. This is not straightforward. We had to jump through some hoops to get to this point, and you can see that there are some host components that should be pointed out when we do this, right? Because the control plane exists entirely on the adapter, and typically the LiquidIO comes with 2 10 gig or 25 gig interfaces. They typically get bonded when you are deploying it in an OpenStack deployment. And that does not leave anything for management plane traffic to then be handled by the adapter itself. So you have to rely on the interfaces on the host to do that, right? And then since the control plane does not exist on the host anymore, we had to add a relay agent that allows those packets to then come to the control plane running on the LiquidIO. But again, the bond is managed by OVS. You can do everything that OVS would do typically in any OpenStack using any standard NIC adapter. And beyond the relay agent, there are not too many things that you need to change as far as there's no change to Neutron in this case, for example. And we were able to use the Pike release, and we were able to demonstrate both orchestration using ODL and OVN. There is a patch required for OVN, which we have submitted. And I think Queens should see more acceptance of the LiquidIO OVS offload solution. And ODL does not require any changes except for the relay agent, right? That can then talk to the DB running on the LiquidIO in this case. We had to add a VF representer model to this because Nova really expects those VFs to be visible on the host. But that just serves as the glue for the whole OpenStack model to work. It does not do any slow path processing. That model still continues to use that path that I showed in one of the previous slides. It continues to use the Linux running on the LiquidIO adapter for the slow path processing, and then once the lookup completes, then it comes back to the fast path. Yeah, and this model works with the ODL and OVN with the existing firmware. So some of the advantages, obviously, we benefit from not having to send packets across PCI for the slow path. And when I say slow path, it's basically when you have a miss, you're going to find if the flow can be added to the adapter. You can do host isolation, so the vSwitch can be remotely managed. That's one of the models that has been very useful for our customers. You don't need to make any changes into the host operating system since everything is within the adapter. We can do a firmware upgrade and provide feature updates, fixes, changes to the OVS if you want to move to a newer version that can be handled entirely within the adapter. Or if our customers are customizing and they want changes, their host operating system does not need to be touched. It can be remotely managed. We do support all the tunneling protocols that are supported by OVS, VXLAN, NVGRE, Geneve. There's some work going on with Geneve on the TLV options right now. That's being done. And of course, because we are leveraging the kernel modules for contract and for NATing, we can support that. There are some limitations. I'll go about that in the next slide. But there are certain cons as well, right? Because you have the interfaces bonded and there are only two of them available, and OVS is fully offloaded onto that adapter, the network access for this OVS offload really has to rely on that one adapter, right? So it's basically kind of limiting in that fashion, right? And obviously, we had to make some changes to make OpenStack work with this full offload model. It's not something that the community has been familiar with, but we're working with them to try to solve those problems. I think we were able to get the integration done with minimal changes, and that model hopefully gets accepted. Data plane, of course, once you have feature additions that come up, for example, when we moved, we had an earlier version of OVS that we were supporting, 2.4, and then when we came to 2.6 and contract supported need to be added, obviously we had to change the data plane, right? So it's not a simple move to a new OVS version. There is some work that Cavium has to do to make it useful. And that work really has to come as a firmware update, but it requires us to do that. Obviously, packets are being sent directly into the VM, and therefore you're doing PCI pass-through, and that has issues with line migration of the VM. It cannot do that. But you could potentially route the packets through the host, for example, attach it via VirtIO. You could have the VFs in the host, and then that still allows you to do the VM migration if that's of interest. So looking ahead, we have plans to move to OVS 2.8 in the near future. We will continue on the path to keep up to date with the OVS versions as they come along. But it will be on a delayed cycle, of course, right? So we need to ramp up our activities on that. We do have plans to support the TC flower-based model, but that's going to happen after we move to the next generation ARM-based processors for our LiquidIO adapters. So 2018 should see some activity around that. And we do need to improve our contract implementation. And part of the reasons where they are, while we can still do security groups, the things that are essential for security groups to allow flows to be guarded. Things like TCP sequence number checking, those kind of things don't exist today. And that has its deficiencies. Trying to rely on the kernel contract module for inspecting all the packets every time comes at a cost. So the copy in the data plane allows us to manage security group handling to a certain extent, but then we have some work to do on that regard. There is plans to support eBPF offload as well with the ARM processors. Once we start getting silicon, we may do that. So there may be some benefits in trying to use the eBPF-based offloads as well. So this is a new model. This is something that LiquidIO has been at the lead to try to engage the community with, and this is something that we want to work with the community. And obviously there are some holes that we want to fix. For example, we cannot have the control plane exist on the host and then interact. There is possible TCP-based connectivity is possible, but it's not very conducive to the offload model. There are other things like OVN. When we try to run the OVN controller on LiquidIO, or basically on the host, then it requires the vSwitch T to run on the host as well. But we were able to get past that by running the controller on the LiquidIO itself. So some points to think about. That completes the presentation. Thank you, and I can take some questions.
Great. Let's thank our speaker. So we have time for one question if somebody has one.
Thank you, Manoj. Great talk. One question about the number of VMs running on that and PCI pass-through. Is there any limitations of number of, you said, VF? Is that we can go?
Yeah, definitely. If you want to attach a VF to a VM, then you're bound by the total number of VFs that the adapter can support. For example, LiquidIO 2 can support up to 126 VFs, and therefore, if you're going to run VMs and have each VM have a single VF associated with it, then you're going to have up to 126 VMs that you can schedule on the processors. That's true.
Thank you.
All right, let's thank our speaker again.
All right, thank you.